it. So in this chart, I want to look first at the left-hand side, where we have these apatite mineral grain values and the lunar volcanic glasses, and that, of course, is the work that Alberto Saul and Eric Howry and Jim Van Orman and that whole team have been doing, and then a whole number of people looking at these apatite mineral grains from the moon and finding quite a lot of water, as has been discussed. And so that actually tells us also something about water that's still down there inside the moon in its current source regions. And so from that information about source regions that can be inferred from that magmatic information, there's this wide range, you can see here over on the right, of estimates for whole moon water content, from the very, very dry numbers that are largely being abandoned now, up to some quite wet numbers from the recent day. And then here's a range of whole, oops, lost my pointer, there we go, whole Earth estimates. So wetter than the moon, but not very much wetter than the wettest lunar estimates. Now, I just added this point over here. This is the latest information from the Saul and Howry group about water in volcanic glass, in melt inclusions, and that led them to estimate the current lunar interior whole water, bulk water content at 79 to 490 parts per million. So we're definitely working up toward the whole Earth range. Although I think one good recent estimate for the whole Earth range from Marti in 2012 is 1,000 to 3,000 parts per million. So maybe we're still talking an order of magnitude less. So that's a current day estimate. So the next way to look at what the primordial estimate might be would be to look at the volatile budgets of planetary building blocks, the material that presumably went into building the Earth and the Moon. And so I really love this image from Marti 2012 showing D to H ratio along the horizontal axis and nitrogen isotopes on the vertical axis. You can see the Earth right here in the middle. And so, of course, the argument used to be that water was added late via comets, and all these cometary values up here do not match the Earth's D to H ratio, but then Comet Hartley 2 is within error of D to H, but it still doesn't match in nitrogen isotopes. And so the point here is that Earth's water and other volatiles are best matched by rocky meteorites and not by comets. And so the same axes here on Alexander et al. 2012 with the dashed lines up and down and sideways showing the situation for the Earth value right here in blue. Perhaps the best fitting is not actually the COs, even though they plot right at the Earth value because titanium and chromium isotopes don't work, but the CIs. And so looking, as other people have in these presentations and will in future presentations today, looking at these rocky building blocks as the sources of volatiles during the accretion of these bodies. And so just to talk for a minute about planetesimals, looking at the planetesimals here on the left that accrete to make planetary embryos and finally to planets. A question I think that we all need to be looking at is how do planetesimals retain volatiles and how do they deliver them into growing planets? Is this really a mechanism that can work to produce water in planets right from the time of accretion? So, of course, we look at meteorites. These are fragments of planetesimals. These are meteorites. Some that are undifferentiated, unmelted, and some that are differentiated into igneous silicates and iron, nickel, metal. And we know that many of the bodies that accreted into embryos and then finally into planets were differentiated, and so we need to look at what the volatile contents that could possibly be carried by them into the growing planets would be. So here's an example of a planetesimal that is undifferentiated. It's been heated and metamorphosed, but not actually melted. And then this is something like Vesta that's melted entirely and formed a core and an igneous mantle. But we also think maybe there were bodies like this one that has melted on the inside from aluminum-26 but retained an undifferentiated chondritic crust. Or possibly here where the magma has flooded the surface but there's still undifferentiated materials inside. And so the question that I'm asking here is how much of that critical volatile content can be retained in bodies that have melted and differentiated in this way? So this is something that Ed Young has looked at extensively in what is the water-rock interaction. Because as you heat up these chondrites, first they melt the ices, and then water and other volatiles start to percolate through them. And what he found was that in bodies smaller than 60 kilometers, fluid would just percolate around on the inside and really not be lost through the surface. And so small warm bodies would retain all of their volatiles. And then if you look at larger bodies where there's a larger gravitational driving force, bodies larger than 60 kilometers, the fluid departs so fast that the minerals in their path aren't even metamorphosed. And so heating up to the silicate melting point in these little bodies might take 100,000 or 200,000 years, but the fluid is percolating away at 100 to 1,000 kilometers per year. And so the point that I want to make here is that if you look back at a body like this one, its interior should be very, very dry, but its crust, and even in this one, its crust could be filled with the fluids that have migrated out of the interior. And so I think even in differentiated bodies, there's a good chance of retaining some good amount of water. And here's data from meteorites with water on the vertical axis and carbon on the horizontal axis. And the thing to notice here is that these orange spots are achondrites. These are silicates that have from bodies that melted and differentiated, and even they are not completely dry. This group that I'm pointing at right now has about 1,000 parts per million of water. And if you recall, the best new estimate for the bulk current Earth is 1,000 to 3,000 parts per million. And so even if these bodies were built from achondritic meteorites, differentiated ones, the bodies that were the progenitors for them, they could have brought enough water into the bodies that all of this water and other volatiles we're seeing on Earth and Moon are primary from accretion. So next, I want to talk a little bit about retention of volatiles during planet building. And then the last, these are the 4 ways I really thought we could look at what are the primordial estimates. The current volatile budgets of the Earth and Moon, the volatile budgets of these planetary building blocks, which we just looked at, how volatiles are retained during the planet building process, and then finally loss of volatiles over the age of the solar system. And I don't have very much to say about loss of volatiles over the age of the solar system. There's some very nice work going on right now about atmospheric stripping and these kinds of questions, and this is definitely a direction that a lot of us need to work more in. So let me just talk mainly about number 3 here, retention. So the big message here is that planets retain volatiles during accretion, even during giant accretionary impacts. And maybe the poster child for volatile retention during planetary building through giant impacts is helium, because we know that we have primordial helium deep inside the Earth now that had to have been delivered during impacts, and yet it has stayed. And so if planets can retain helium during giant impacts and accretion, then surely they can also retain water and carbon. And I'll just mention for a moment, there's a lot of work about degassing from magma oceans. So I've worked on this, and Jim Casting and Kevin Zonley, and of course Yutaka Abe and Genda and all of their group in Tokyo. And the assumption has largely been here on the left that the magma ocean would just degas gradually all the time that it was solidifying after the last big impact. But bubble breakup creates small bubbles, and small bubbles remain entrained and don't degas in the turbulent magma ocean. And so we actually suggest, as this work being done by Jenny Sukala, who's right now at Harvard, that a very high degree of supersaturation is required before foamy, bubbly magma ocean liquids can rise almost like diapirs and degas in early atmosphere. And what this means, if we're right, is that even more volatiles will be retained inside the planet because solidification is going to have to go to 70 or 80% before this big degassing event is going to occur. And so it's another way for planets to hold on to their volatiles. And so finally, let me return to this slide. Let's see. to this slide with water or hydroxyl on the vertical axis. And the thing that I want to point out here is that here with this red star, this is the estimate that that Saul and Howery and their group made in 2011 for the bulk lunar interior water content based on the measurements that they made from samples that were erupted about 3 billion years ago. And the same year, Tim Grove and I did a theoretical modeling paper on how much water could you put in a fractionating lunar magma ocean and still meet all the petrologic requirements of iron metal and requirements for hydrogen to stabilize water. And we actually came up with the same number that Eric Howery got from looking at melt inclusions and glasses. And so I wonder if we're not actually beginning to zero in on what the primordial water content of the moon was, in fact, something in the 100 or hundreds of parts per million of water, less than the Earth, but definitely not zero. And so that's the whole talk that I wanted to give today. Thanks very much.
Thanks, Lindy. Does anybody have any questions? You can see there are some people typing. Multiple, indeed. Oh, lots of questions.
Hi, Sarah. Nice to see you.
Hey,
You're just up the road. Yeah.
I know, right? Okay, Satadru has a question. What is the mechanism that is responsible for retention of volatiles after a giant impact?
Well, so it's been said that, and I guess this was the original idea for making a dry moon, that volatiles would be lost into a plasma or a gas phase, and then they would be swept away preferentially. But I think that there's good reason to think that some material is not sent all the way to the plasma or the gas phase, and volatiles will be retained in whatever melt and solid that is. But also, it's possible for that material to condense directly to a liquid. It doesn't necessarily have to go through the solid phase. If it condenses to liquid, then it's even easier for it to retain volatiles. I actually think it's much harder to completely dry things out. That would be my almost too simple answer for that.
There's also a question from Sarah. Can you say something about H versus OH versus H2O?
Yeah, I think that there's good reason to think that a lot of what was happening on the moon was H and OH versus H2O, possibly a lot of H, because that helps to explain the pervasive iron metal in the surface samples. For example, you can make equilibrium between hydrogen, hydroxyl, and water if you've got enough H. But that's maybe the only sensible thing that I have to say about H versus OH versus H2O.
Okay, from Steve Desch, he's responding to Satadru. The better question is, what is the mechanism for volatile loss after a giant impact?
Yeah, that's right. You know, how could you possibly really completely dry everything out? You have to lose all of the structurally bound OHs and Hs from every different phase, plus all the other volatiles.
Okay. Thank you very much, Lindy. I think we got to move on to